Welcome to class, everyone. I'm your professor for today's Masterclass Explainer. We're going to dive straight into the invisible technology that literally keeps our modern world powered. Flexible AC transmission systems, or as we call them, FACS. We'll be unpacking the sheer physics of the grid and discovering exactly how engineers prevent massive blackouts. We're building a complete, ground-up understanding of how we control modern power grids, and yes, we'll be breaking down every single diagram and all the math that makes it happen. Let's get right to it.
Okay, so here's our syllabus for today's lecture. First, AC grid fundamentals. Then, pre-FACS limitations, followed by FACS taxonomy and topologies. After that, we'll hit VSC dynamics and control, and finally, we'll wrap up with system implementation.
Moving into Part 1, AC Grid Fundamentals. This is where we build our foundational understanding of macroscopic grid vulnerabilities.
Starting with Slide 1. Take a look at this network diagram detailing the macroscopic grid challenge. On the far left and right, we've got these remote generating stations feeding into massive high-voltage transmission corridors. Those lines weave into a highly complex, interconnected mesh network right before they reach the dense urban load centers in the middle. Now, the vulnerability note here points out an inherent trade-off. The absolute greatest strength of this interconnected mesh is that it exploits load diversity and shares generation reserves. But that's also its fatal flaw. Because, as this diagram shows, disturbances in interconnected meshes can propagate. A single fault in one localized area can literally ripple across the entire network.
On to Slide 2. Let's examine the fundamentals of AC power transmission. We have two diagrams here. Diagram A showing a generating station, and Diagram B supplying a load. In both cases, power flow is entirely at the mercy of the line's natural physical properties. Now let's meticulously derive equation 1.1. This equation proves that uncontrolled power flow is naturally determined by the voltage difference, the bus angles, and the natural reactance. Essentially, in conventional AC lines, you have zero active control over the current path. Bus angles just adjust automatically to load changes. You get exactly what physics gives you.
Moving to Slide 3. Let's trace this mesh flow problem diagram. Power flow strictly follows Kirchhoff's voltage law. It doesn't care about our contractual agreements, it just takes the path of least resistance. Now break down the tie-line dynamics equivalent circuit below that. The core engineering takeaway here is that dynamic tie-line power flow is driven by mismatches between area generation and area load. During unpredictable dynamic disturbances, these tie lines are left completely uncontrolled and become highly vulnerable to tripping.
For Slide 4, let's parse the axes of this maximum power transfer chart. The y-axis is power transfer, and the x-axis is line length. Notice the flat green line at the top? That's our thermal limit, restricted simply by the current carrying capacity, basically how hot the physical wires can safely get. But contrast that with this plunging orange curve. That is our stability limit. As you can see from equation 1.2 in the text, as lines get longer, their natural reactance increases, which mathematically constrains and decays our stability limit. It becomes a massive bottleneck for power transfer.
Moving on to Part 2, Pre-FACS Limitations and FACS Taxonomy. What's really interesting here is how we transition from these inherent physical limitations to the structural taxonomy of modern controllers designed to break them.
On Slide 5, let's look at conventional control methods. We have three pre-FACS circuit diagrams here. First, series compensation, which artificially shortens a line's natural reactance. Second, the phase shifting transformer, or PST, to manually tweak voltage angles. And third, reactive support, injecting reactive power right at the receiving end. If you trace the derivations of equations 1.4 through 1.7, they mathematically prove that by applying these methods, power transfer can dynamically be doubled. However, we absolutely must read this crucial note. These mechanical solutions can introduce subsynchronous resonance, or SSR, instability.
Announcing Slide 6. Here is the official Flexible AC Transmission Systems Taxonomy table. The exact definition of FACS provided is that they are alternating current transmission systems incorporating power electronic-based controllers. Let's exhaustively process this 2x4 matrix. We are comparing older variable impedance controllers against modern VSC-based ones. Across the rows, we see they can be connected in shunt, series, or combined configurations. Depending on the exact grid problem, operators will select a specific device from this matrix, like an SVC for shunt variable impedance or a UPFC for combined VSC control.
Continuing to Slide 7, this brilliantly illustrates the divide between these two technologies.
Let's compare the specific circuit symbols and read the bulleted characteristics for both. On the left, variable impedance uses standard thyristors. They are cheaper and have reduced switching losses, but they're fundamentally limited. On the right, VSC characteristics highlight superior capabilities. They use modern transistors, they're highly compact, they can supply active power if connected to a source, and critically, they maintain full reactive current even when grid voltages plummet. Absolute game changers.
That brings us to Part 3, VSC topologies, dynamics, and control. The crucial point now is understanding the internal mechanics of these voltage source converters. We are going to deconstruct them circuit by circuit.
Announcing Slide 8, let's verbally trace every block, signal, and connection for these three figures. Figure 1.7 is the STATCOM topology. Acting in a shunt or parallel connection, it draws DC voltage to inject shunt current. Next is Figure 1.8, the SSSC, which connects directly in series with the AC client line. And finally, Figure 1.9, the Unified Topology, or UPFC. This merges both shunt and series converters, linking them with a shared DC capacitor. The engineering meaning here is huge. It allows real power to flow freely between terminals, giving unprecedented simultaneous control over both voltage and power flow.
Proceeding to Slide 9. Let's recreate the visual flow of this three-phase VSC diagram. How does it actually synthesize AC from DC? It uses 6 high-speed switches, shown here connected to a DC capacitor. By precisely opening and closing these 6 switches, we literally build a smooth, alternating voltage from scratch. Now read the System Control Core note at the bottom. It details the phase lock loop, or PLL, which perfectly synchronizes the injected AC voltage's phase and frequency with the main grid bus.
For Slide 10, let's examine this single-phase half-wave converter diagram. When we systematically derive equations 1.8, 1.9, and 1.10, we see the mathematics of triplen harmonic cancellation. Basically, a simple square-wave switching scheme derives fundamental peak components and naturally cancels certain harmonic distortions. But we need to read the strict constraint note here regarding square-wave switching. It allows us to control the phase angle of the injected voltage, but we cannot independently control its magnitude.
Moving to Slide 11 to solve that exact problem, let's analyze the PWM, pulse width modulation, waveform, in Figure 1.12. Notice the varying widths of those gray pulse blocks? By varying those widths, we trick the system into seeing a smooth, average sinusoidal wave. Stepping through the mathematics of equations 1.111 and 1.12 unlocks our magnitude control. And explaining the bottom note, by independently controlling this modulation index alongside the phase angle, a VSC achieves full vector control.
Announcing Slide 12, let's trace the UPFC equivalent circuit. Notice the voltage and current sources here. When we rigorously explain equations 1.13 through 1.16, they prove something incredibly elegant about complex power controls. Neglecting minor power losses, these equations mathematically guarantee that the real power drawn by the shunt converter perfectly matches the real power supplied to the series converter. It's a completely balanced ecosystem. Real power in equals real power out.
On Slide 13, let's look at how this is managed. We need to read completely across every single row of this table, mapping operational constraints to control variables. Whether managing the startup sequence, regulating DC link voltage, or orchestrating active and reactive power flow, every single desired grid outcome is mathematically tethered to a specific control variable. Adjacent to the table is the RLC circuit block diagram. We can clearly see how the components, the inductors, capacitors, and switches, physically execute the logic driven by those control variables.
Which brings us to Part 4, System Implementation and Distribution Applications. We're in the final stage of our lecture, mapping these rigorous mathematical concepts to system-wide physical implementations and distribution-level devices.
Announcing Slide 14, let's systematically review all 6 benefit panels for FACS implementation, reading the text exactly as presented. Panel 1, Optimal System Operation Reducing Power Losses. Panel 2, SSR Mitigation. Panel 3, Transient Stability, Dampening Oscillations. Panel 4, Dynamic Overvoltage Control. Panel 5, Voltage Profile Improvement. And Panel 6, Thermal Limit Exploitation, meaning we can confidently push line loading right up to its strict thermal limits because of the fast controllability FACS provides.
Reaching our final diagram on Slide 15. Here, we see FACS applied at the distribution level through custom power devices, or CPDs. Let's trace the power quality problem through this disturbance taxonomy tree. We have transients, variations, distortion, and unbalance. every single one of these problems connects explicitly to a tailored solution. The DStatCom eliminates harmonics and unbalance. The Dynamic Voltage Restorer, or DVR, isolates the load from variations like sags. And the Unified Power Quality Conditioner, or UPQC, handles everything as the ultimate balancing act.
To fulfill our academic rigor, I am formally conducting the end-of-lecture verification right here. We have processed all 15 slides sequentially. Total slides in PDF, 15. Total slides explained, 15.